The headline exploded across the internet like a supernova. Scientists had detected a parallel universe, not a theoretical possibility tucked away in equations, not a philosophical thought experiment, a real, honest-to-goodness parallel universe where time runs backward, where the laws of physics operate in reverse, where every choice you never made has been made, where another version of you is living out an entirely different life. The story spread like wildfire across social media, news sites, and YouTube channels. Millions of people watched videos claiming that NASA had confirmed the existence of a mirror reality sitting right next to our own. Comment sections filled with reactions ranging from excitement to existential dread. Some people wondered if they could somehow contact their parallel selves. Others questioned what this meant for free will, for the nature of reality itself. The viral spread was extraordinary in its speed and reach. Within hours of the first sensational headlines, the story had been shared millions of times. Twitter threads dissected the implications. Reddit communities debated what it meant for quantum immortality and the nature of consciousness. Facebook groups dedicated to science and science fiction lit up with discussions. YouTube creators raced to produce videos explaining the discovery, many getting fundamental details wrong but garnering hundreds of thousands of views. The algorithm loved it. Content about parallel universes satisfied our deep hunger for the mysterious and world-shattering, that desire to believe we're living through a moment of profound discovery. The psychological appeal is understandable. The idea of parallel universes touches something fundamental in the human psyche. We all carry regrets, roads not taken, decisions we wish we could revisit. The thought that somewhere, somehow, another version of us made different choices offers a strange comfort. It means that, in some sense, all possibilities are realized. The life you didn't live is being lived by another you in another reality. That job you turned down, you took it in another universe. That person you didn't ask out, you're married to them somewhere in the multiverse. It's a deeply appealing notion, even if it raises as many troubling questions as it answers. But here is the problem with viral science stories. They almost never tell you the whole truth. And this one got so twisted in translation that the actual scientist had to come forward and say, "Wait, hold on, that's not what we discovered at all." The gap between the sensational headlines and the actual research was not just a difference of degree, but of kind. What began as a careful scientific paper proposing one possible theoretical framework among many to explain puzzling data became, through a game of telephone-spanning journalism, social media, and content creation, a definitive announcement of revolutionary discovery. Before we dive into what really happened, before we explore the genuine science of parallel universes and whether they might actually exist, we need to understand how a balloon flying over Antarctica sparked the biggest physics misconception of the modern era. This is the story of how real science gets transformed into science fiction by the time it reaches your screen. This is the story of neutrinos behaving strangely in the ice, of theoretical physicists proposing wild explanations, and of a media machine that couldn't resist turning speculation into sensational headlines. And along the way, we're going to explore the actual mind-bending science of parallel universes. Because while the viral story was wrong, the real science is somehow even stranger. If you're ready to separate fact from fiction and explore the genuine mysteries of our cosmos, hit that like button and subscribe. Let's begin. Antarctica is not just the coldest place on Earth. It's also one of the best laboratories we have for detecting some of the universe's most elusive particles. Hidden beneath miles of ice, buried in one of the most inhospitable environments on the planet, scientists have constructed massive detectors searching for neutrinos, those ghost particles that pass through matter as if it weren't even there. But this story doesn't begin underground. It begins in the sky, suspended from a helium balloon floating more than 22 miles above the frozen continent. The Antarctic Impulsive Transient Antenna, mercifully abbreviated to ANITA, looks like something assembled from spare parts in a science fiction movie. Imagine a gondola bristling with 48 radio antennas, all pointed downward at the ice below, connected to sensitive electronics and powered by solar panels. This strange contraption circles Antarctica on the stratospheric winds, riding currents of air in the thin upper atmosphere, using the entire continent as a gigantic neutrino detector. The concept is brilliant in its simplicity. When ultra-high-energy neutrinos slam into the Antarctic ice, they create a shower of secondary particles. This shower produces a burst of radio waves, a kind of electromagnetic scream that propagates through the ice. ANITA, floating high above, listens for these screams. The physics behind radio detection is fascinating and somewhat counterintuitive. When a high-energy particle travels through a dielectric medium like ice faster than light can travel through that medium, it produces a shock wave of electromagnetic radiation. This is similar to how a supersonic jet creates a sonic boom when it exceeds the speed of sound in air. The phenomenon, discovered by Russian physicist Pavel Cherenkov, produces visible blue light in water. In ice, it also produces radio waves at frequencies ANITA can detect. This radio emission, predicted in 1962 by Gurgen Askarian and confirmed experimentally in 2001, makes it possible to search for neutrinos using radio telescopes rather than optical detectors. The advantage of radio detection is range. Radio waves can travel through ice much farther than optical light, which gets scattered and absorbed. ANITA, from its high vantage point, can monitor over 1 million cubic kilometers of ice, an impossibly large volume to instrument with traditional detectors. The ice itself becomes the detector medium, a natural resource Antarctica offers in abundance. By flying above the continent for weeks at a time, ANITA can observe this enormous volume continuously, searching for the rare flash that signals a cosmic neutrino collision. The experiment launched for the first time in 2006, the brainchild of physicist Peter Gorham from the University of Hawaii. He and his team had spent years developing the technology, proving that radio detection could work for finding these cosmic messengers. The design involved careful engineering to discriminate between genuine neutrino signals and background noise from human-made radio sources, lightning, and other natural phenomena. Each antenna had to be precisely calibrated. The electronics had to operate reliably in the extreme cold and low pressure of the stratosphere. The balloon itself, as large as a football stadium when fully inflated, had to maintain altitude and stability while circling the pole. Neutrinos at the energies ANITA hunts for are incredibly rare. They're produced when the highest energy cosmic rays, particles accelerated to mind-boggling speeds by the most violent events in the universe, collide with the cosmic microwave background radiation. These collisions, scattered across billions of light-years, send neutrinos screaming toward Earth. Most pass through our planet like it's made of empty space, which from a neutrino's perspective it basically is. But occasionally, very occasionally, one hits something. ANITA's mission is to catch those rare interactions, measuring their energy and direction to learn about the cosmic accelerators producing them. The technical challenges are substantial. Radio signals from neutrinos are faint, fleeting, and buried in noise. The ANITA team had to develop sophisticated signal processing algorithms to identify genuine events. They had to account for how radio waves propagate through ice of varying density and temperature. They had to understand how the balloon's motion and the Earth's rotation affected their observations. Every aspect of the experiment required meticulous attention to detail. One error in calibration, one unaccounted source of background, could lead to false detections or missed events. ANITA's first 3 flights detected what they were supposed to detect: cosmic rays slamming into Earth's atmosphere, producing showers of particles, generating radio pulses. Everything worked as expected. The team refined their methods, calibrated their instruments, and prepared for more ambitious flights. They published papers describing their techniques and initial results. The scientific community took notice. Radio detection of ultra-high energy neutrinos was proving viable, opening new possibilities for studying the highest energy processes in the cosmos. But during ANITA's 3rd flight in 2016, something impossible happened. The detectors picked up a signal that looked like a neutrino interaction. But this neutrino wasn't coming from space. It was coming from below, emerging from deep within the Earth itself, shooting upward through the ice toward the balloon. The polarization of the radio signal, the timing, the frequency characteristics, all matched what you'd expect from a neutrino-induced shower. Except for one thing: the direction. It was pointing up instead of down. This shouldn't happen. Can't happen actually, according to everything we know about particle physics. Let me explain why in more detail. Neutrinos interact so weakly with matter that they can pass through light years of solid lead without being stopped. At low energies, like the neutrinos from the Sun, their interaction probability is infinitesimal. You could stack Earths like pancakes from here to Alpha Centauri, and a solar neutrino would pass through all of them without hitting anything. But at ultra-high energies, the kind ANITA detects, their interaction probability increases dramatically. The cross-section, the effective target size, grows with energy. A neutrino carrying 1,000,000 times more energy than particles in the Large Hadron Collider has a much larger cross-section, a much higher chance of hitting something. When you calculate the probability that such a neutrino could pass through the entire diameter of Earth and emerge on the other side, the numbers are astronomically small. The calculation involves integrating the interaction probability along the neutrino's path through varying densities of rock, magma, iron core. Each layer presents opportunities for interaction. The cumulative probability of avoiding all interactions approaches zero. You would need to observe for millions of years, maybe longer, to expect to see even one such event by random chance. And yet there it was in the data. An upward-pointing event that looked for all the world like an ultra-high-energy neutrino emerging from the ice. The team checked everything, recalibrated, ran simulations, analysed the signal from every possible angle. The event remained inexplicable. Then, in 2018, during ANITA's 4th flight, it happened again. Another anomalous upward-pointing event. Another signal suggesting a particle that had somehow traversed thousands of miles of rock and iron without being stopped. The probability of seeing even one such event by chance was minuscule. Seeing two? That moved from unlikely to deeply strange. The scientific process that followed demonstrates how research should be conducted, even if the eventual media coverage would betray these careful methods. The ANITA team didn't immediately claim a discovery. They didn't call a press conference or issue breathless announcements. Instead, they did what good scientists do. They questioned everything, tested alternatives, and invited scrutiny from colleagues. First, they had to rule out terrestrial sources. Could these signals be reflections of radio transmissions from human sources? Antarctica hosts research stations. Aircraft sometimes fly over. There are communication satellites. The team analysed the frequency spectrum, the polarization, the pulse shape. They compared the anomalous events to known radio sources. The characteristics didn't match. These weren't reflections of human-made signals bouncing off the ice. The frequency content was wrong. The pulse duration was wrong. The polarization was wrong. Could the signals be from lightning? Antarctica experiences electrical storms, though rarely. Lightning produces radio pulses. But lightning pulses have distinctive characteristics. They're broadband, they occur in clusters, they have specific polarization patterns. The anomalous ANITA events didn't match. The team could confidently exclude lightning as an explanation. The signals were too narrowband, too isolated, and had the wrong polarization characteristics for atmospheric electrical discharges. What about cosmic ray air showers? These are well understood and common. When a cosmic ray proton or heavier nucleus slams into Earth's atmosphere at relativistic speeds, it creates a cascade of particles. This cascade, called an extensive air shower, produces radio emission through multiple mechanisms. ANITA sees these all the time. They're normal background. But air showers develop in the atmosphere, above the surface. The radio pulses from air showers arrive at ANITA from above, not below. The anomalous events were coming from below, from the ice, pointing upward. This geometry was incompatible with standard air showers, unless perhaps the air shower had somehow reflected. Radio waves can bounce off surfaces. The Antarctic ice sheet is mostly horizontal, stretching for hundreds of miles in every direction. Could a downward-pointing air shower signal reflect off the ice surface and reach ANITA appearing to come from below? This was a possibility the team took very seriously. They analysed the signal characteristics that would distinguish a reflection from a direct upward-travelling signal. Reflections typically invert the phase of the electromagnetic wave, flipping the polarity. The anomalous events didn't show this phase inversion. Their polarity matched what you'd expect from a direct upward-travelling shower, not a reflected downward one. But subsurface reflections might work differently. Ice is not uniform. There are density variations, layers where snow transitions to firn transitions to solid ice. There are interfaces deep underground where properties change. Radio waves encountering these interfaces can reflect, and under certain conditions, they might not undergo the standard phase inversion. This possibility became a leading candidate explanation, and sparked extensive research into Antarctic ice structure and radio wave propagation. Peter Gorham and his colleagues published their findings in scientific journals. They were careful, measured, precise in their language. They described the observations accurately. They noted that the events were inconsistent with standard model physics. They presented the evidence they had for ruling out mundane explanations. They acknowledged that they didn't have a good explanation. And critically, they invited the broader physics community to help solve the mystery. This is how science is supposed to work. You observe something unexpected, you report it honestly with all caveats and uncertainties, and you admit when you don't understand what you're seeing. Other scientists then propose explanations, design follow-up experiments, test hypotheses. The process is collaborative, iterative, and deeply skeptical of extraordinary claims. The response from the broader community was swift and energetic. Within months, dozens of theoretical papers appeared on the IceCube preprint server, the repository where physicists share work before formal peer review. Each paper proposed different explanations for the anomalous events. Some invoked new physics, sterile neutrinos, supersymmetric particles, dark matter interactions. Others suggested exotic astrophysical scenarios, neutrinos from cosmic strings, neutrinos produced by primordial black holes evaporating through Hawking radiation. Still others proposed more conventional explanations involving ice properties, radio propagation effects, or statistical flukes. Peter Gorham and his colleagues published their findings in scientific journals. They were careful, measured, precise in their language. They described the observations accurately. They noted that the events were inconsistent with standard model physics. They acknowledged that they didn't have a good explanation. And they invited the broader physics community to help solve the mystery. This is how science is supposed to work. You observe something unexpected, you report it honestly, and you admit when you don't understand what you're seeing. Other scientists then propose explanations, design follow-up experiments, test hypotheses. The process is collaborative, iterative, and deeply skeptical of extraordinary claims. But between the publication of careful scientific papers and the explosion of headlines across the internet, something went terribly wrong. The ANITA anomalies became, in the public mind, proof of a parallel universe. To understand how this happened, we need to follow the chain of communication from research paper to news article to viral video. Because somewhere along that chain, nuance got lost, speculation got presented as fact, and the distinction between a puzzling observation and a revolutionary discovery completely evaporated. In the aftermath of ANITA's strange detections, physicists around the world began proposing explanations. This is normal, this is healthy, this is how science progresses. When confronted with data that doesn't fit existing models, theorists explore possibilities, even wild ones. Creative thinking, theoretical imagination, pushing boundaries, these are essential to scientific discovery. The key is maintaining appropriate epistemic humility, clearly distinguishing between speculation and established fact. One research group, led by Louise Ancordogui and collaborators, published a paper in 2018 with an intriguing idea. What if, they asked, the universe we observe is only half of a larger reality? What if the Big Bang didn't just create one universe expanding forward in time, but two universes, moving in opposite temporal directions? The paper, titled Upgoing ANITA Events as Evidence of the CPT-Symmetric Universe, appeared in the journal Letters in High Energy Physics. It was brief, speculative, and carefully hedged with qualifiers. This concept draws on something called CPT symmetry, one of the fundamental principles of particle physics. CPT stands for charge, parity, and time. The principle states that the laws of physics should remain unchanged if you simultaneously flip the charge of every particle, mirror reverse space, and run time backward. It's a beautiful mathematical symmetry that has held up in every test we've thrown at it. The principle emerges naturally from quantum field theory and special relativity. Violating CPT would require overturning some of the most fundamental frameworks in physics. The researchers wondered whether this symmetry might manifest not just in equations but in physical reality. Perhaps our universe has a mirror twin, identical in every way except that time runs in the opposite direction. In this mirror universe, what we call the Big Bang would be experienced as a kind of big crunch in reverse. Cause and effect would be inverted, entropy would decrease rather than increase from their perspective. From our perspective, time in this parallel universe flows backward. From their perspective, if conscious observers could exist in such a place, our time would be flowing backward. It's a mind-bending concept that raises immediate questions about the nature of causality and consciousness. Can you have consciousness in a universe where entropy decreases? What would subjective experience feel like in a time-reversed reality? Would memories point toward the future rather than the past? These philosophical puzzles aside, the paper suggested that perhaps the ANITA events were neutrinos from this mirror universe, somehow interacting with our detectors in unexpected ways. The theoretical machinery was sophisticated. The authors constructed a model where the Big Bang creates a pair of universes, related by CPT transformation. Both universes expand away from the creation event, but in opposite temporal directions. Particles in one universe have antiparticle counterparts in the other. The model aimed to preserve certain symmetries, while allowing for the possibility of cross-universe interactions under very specific conditions. The ANITA anomalies, they suggested, might be rare instances where the barrier between universes becomes permeable, allowing particles to cross from one reality to the other. Now, here's where things go sideways, where the careful scientific process breaks down in communication. The researchers themselves were careful in their paper. They presented this as one possible theoretical framework among many. They used conditional language, could, might, if this model is correct. They acknowledged it was speculative. They emphasized that more evidence would be needed. The abstract of their paper doesn't claim to have proven anything. It proposes a hypothesis and explores its consequences. But when science journalists got hold of the paper, the qualifier started falling away like autumn leaves in a strong wind. A Story in New Scientist, a respected popular science magazine, used the headline, "We may have spotted a parallel universe going backwards in time." That word may is doing a lot of heavy lifting, grammatically preserving a fig leaf of conditionality while psychologically suggesting something much stronger. The article itself was more careful, explaining the speculative nature of the hypothesis and noting that other explanations existed. But headlines are what people remember, what gets shared, what shapes perception. Other outlets picked up the story, and with each retelling, the certainty increased like a game of telephone, where each participant adds confidence to the message. May have spotted became have spotted, became discovered, became confirmed. By the second or third iteration, qualifiers had evaporated entirely. The transformation was gradual but inexorable, driven by the incentive structures of modern media. Clicks reward certainty. Ambiguity is boring. Hedged claims don't go viral. Revolutionary discoveries do. By the time the story reached social media and YouTube, it had transformed completely. NASA discovers parallel universe where time runs backward. Scientists confirm mirror reality, proof of alternate dimensions. The algorithm loved it. Videos racked up millions of views in days. People shared the story without reading beyond the headline, as social media analytics consistently show most people do. Comment sections filled with speculation and excitement. Some people discussed the philosophical implications, wondering whether their parallel selves had made better decisions. Others dove into pseudoscience, linking the discovery to every conspiracy theory and mystical belief system imaginable. And the actual scientists, the ones who'd been carefully studying neutrino anomalies, found themselves besieged by questions about a discovery they'd never claimed to make. Peter Gorham received emails from journalists, requests for interviews, questions from family and friends, all asking about the parallel universe ANITA had detected. He had to explain, patiently and repeatedly, that his team had not detected a parallel universe. They detected anomalous signals. The parallel universe hypothesis was one theoretical speculation among dozens. It was far from proven, far from the most likely explanation, and definitely not something the ANITA team was claiming. Peter Gorham, the principal investigator for ANITA, had to go on record multiple times clarifying that his team had not detected a parallel universe. He explained, patiently, that the anomalous events were real, but their interpretation was uncertain. Yes, theoretical physicists had proposed a parallel universe as one possible explanation, but so had dozens of other theories. Some suggested the signals were reflections off subsurface ice layers. Others proposed unknown particle physics. Still others thought there might be experimental artifacts they hadn't yet identified. The parallel universe hypothesis was interesting, sure, but it was far from proven, far from the most likely explanation, and definitely not something the ANITA team was claiming. The correction process revealed deep structural problems in how scientific information flows to the public. Gorham gave interviews to reputable outlets. He explained the situation clearly, emphasizing the difference between detecting an anomaly and discovering a parallel universe. These corrections were published, but they received a fraction of the attention the original sensational story had garnered. The corrective articles didn't trend on social media, they didn't get boosted by algorithms, they didn't accumulate millions of views. The truth, it turns out, is less viral than fiction. This asymmetry creates a persistent problem. Someone who saw the original sensational headline might never encounter the correction. Their mental model of reality has been updated to include "scientists discovered a parallel universe" as a fact. Unless they actively seek out follow-up information, which most people don't, this false belief persists. Over time, it becomes part of the landscape of things they know, indistinguishable from actual established facts. When they encounter references to parallel universes in the future, this false memory serves as confirmation, reinforcing the belief. Psychological research on belief correction shows how difficult it is to dislodge false information once it's embedded. The mere exposure effect means that the more often people see a claim, even in the context of debunking it, the more familiar it becomes, and familiarity often gets confused with truth. The backfire effect, though more controversial, suggests that sometimes presenting corrective information can actually strengthen false beliefs if the correction is perceived as attacking the person's identity or worldview. The ANITA parallel universe story became a case study in science communication failure. It illustrated every pitfall: the simplification of complex research, the loss of nuance through successive retellings, the algorithmic amplification of sensationalism, the asymmetry between viral misinformation and boring corrections, and the persistence of false beliefs despite corrective efforts. But by then, the damage was done. The viral story had taken on a life of its own, replicating across the internet like a particularly infectious meme. It appeared in videos years after the original reports, presented as fresh news. Content creators who didn't do their homework recycled the story, sometimes adding their own embellishments. The parallel universe narrative became part of internet lore, a story everyone knows, even though it's false. And here's the frustrating part for scientists. Once a misconception gets embedded in popular culture, it's almost impossible to dislodge. You can publish corrections, give interviews, write explanatory articles. But corrections don't go viral the way sensational claims do. The truth is boring compared to the fiction. A parallel universe discovered? That's exciting. It confirms our sense that reality is stranger than we thought, that science is on the verge of paradigm-shifting revelations. A neutrino anomaly that probably has a mundane explanation involving ice reflections. That's just another day at the office for physicists. It doesn't satisfy our hunger for the extraordinary. The ANITA controversy highlights a fundamental problem in how cutting-edge science gets communicated to the public. Real research is tentative, full of uncertainties and qualifications. Scientists speak in probabilities, not certainties. They hedge their claims, acknowledge alternative explanations, and emphasize the need for more data. This careful language reflects the actual epistemology of science. We build knowledge incrementally, testing hypotheses, ruling out alternatives, gradually narrowing the space of viable explanations. But this careful language doesn't translate well to headlines designed to grab attention in a crowded media landscape. Editors face pressure to make stories compelling. Journalists work under tight deadlines, often without deep expertise in the subjects they're covering. They rely on press releases which themselves may oversimplify the research. By the time a finding reaches social media, it's been filtered through multiple layers of simplification, each shearing away nuance and uncertainty. In December 2024, Newsweek and other outlets had to publish articles explicitly debunking the parallel universe claims, noting that the story was based on old research from 2020 and that no new evidence had emerged. The IceCube experiment, another neutrino detector in Antarctica, had searched for sources that could explain the ANITA anomalies and found nothing. The most likely explanation, according to current thinking, involves radio signal reflections from subsurface ice structures, not revolutionary physics, and certainly not parallel universes. But even as these corrections circulated, the original viral story continued to spread, zombie-like. refusing to die. The IceCube investigation deserves special attention because it demonstrates how science uses multiple independent methods to test hypotheses. IceCube is a massive neutrino telescope, fundamentally different from ANITA in design and methodology. While ANITA flies above the ice looking for radio signals, IceCube sits deep within it, a cubic kilometre of Antarctic ice instrumented with over 5,000 optical sensors arranged on 86 vertical strings. These sensors watch for the faint blue flashes of Cherenkov light produced when neutrinos interact with atoms in the ice. IceCube primarily detects lower energy neutrinos than ANITA targets, ranging from about 10 giga-electron-volts up to a few peta-electron-volts. But there's overlap in the energy ranges, and IceCube has excellent directional resolution. If the ANITA events came from a genuine astrophysical neutrino source, a supernova or active galactic nucleus, or some other cosmic accelerator producing a beam of ultra-high energy neutrinos, then IceCube should have seen some signal from that direction, perhaps at slightly lower energies. The IceCube collaboration conducted a targeted search, examining 8 years of data looking for coincidences with the ANITA anomalous events. They focused on the sky directions corresponding to the ANITA detections, searching for any excess of neutrinos from those regions. They used multiple time windows from hours to years, accounting for the possibility that the source might have been transient or persistent. They analysed different energy ranges, trying to catch any signal that might have been missed in previous searches. The result? Nothing. No significant excess of neutrinos from the ANITA directions. No point sources, no extended sources. The lack of detection was statistically significant enough to rule out many of the more exotic explanations for the ANITA events. If these had been genuine ultra-high energy neutrinos from a powerful cosmic source, IceCube should have seen them. The absence of a signal suggested that either the ANITA events weren't neutrinos at all, or they were from some extremely specific and unlikely scenario that produced ultra-high energy tau neutrinos, while somehow avoiding lower energy production, which doesn't match theoretical models of neutrino generation. This non-detection didn't definitively solve the mystery, but it significantly constrained the space of explanations. It ruled out the simplest astrophysical scenarios and strengthened the case for more mundane explanations involving instrumental effects or ice properties. The scientific process was working exactly as it should. Independent experiments cross-checking results. Hypotheses being tested and eliminated or supported, the range of viable explanations narrowing. The most likely explanation, according to current thinking, involves radio signal reflections from subsurface ice structures. Antarctica's ice sheet is not perfectly uniform. As snow accumulates year after year, it compacts into firn, a granular, dense snow, which eventually transitions to solid glacial ice. This transition happens gradually over hundreds to thousands of years, creating layers with different densities and different dielectric properties. Additionally, the ice contains various features: density inversions, where a layer of less dense ice sits below denser material, wind crust formed by surface processes, volcanic ash layers from ancient eruptions, zones of different crystal structure. All of these can affect radio wave propagation. When a radio wave encounters an interface between materials with different dielectric constants, some of the wave reflects. The details of reflection, including whether the wave undergoes phase inversion, depend on the specific properties of the interface. The ANITA team had originally thought they could distinguish reflections from direct upward-pointing signals by looking for phase inversion in the polarization. Reflections off a simple ice-air interface do show this inversion, but subsequent theoretical work and laboratory experiments suggested that certain types of subsurface interfaces might reflect radio waves without the expected phase inversion. If the ANITA signals bounced off such an interface deep within the ice, they would appear to come from below while actually originating from cosmic ray air showers above. Research groups began modelling Antarctic ice structure in detail, using radar surveys and ice core data to map the layers. They ran simulations of radio wave propagation through these complex structures, testing whether subsurface reflections could produce signals matching what ANITA observed. The results were promising. Under certain geometric and material conditions, subsurface reflections could indeed mimic upward-pointing neutrino events. The probability calculations showed this was rare but not impossibly so, compatible with seeing a few events in ANITA's observing time. This explanation is less exciting than new physics or parallel universes. It's mundane, a matter of understanding ice better and accounting for propagation effects. But mundane explanations are often correct. Science has a long history of mysteries that seemed revolutionary, turning out to have prosaic solutions once better data was collected or better models were developed. To understand why the ANITA detections were so surprising and why they sparked such intense speculation, you need to understand neutrinos themselves. These particles are the universe's ultimate minimalists. They have almost no mass, barely larger than zero. They carry no electric charge. They don't participate in the strong nuclear force that binds atomic nuclei together, nor in the electromagnetic force that governs chemistry and light. They interact only through the weak nuclear force and gravity at their tiny mass is utterly negligible. This makes them extraordinarily difficult to detect. Neutrinos are ghostly in the truest sense. They're born in the nuclear furnaces of stars, in the violent collapse of supernovae, in the decay of radioactive elements deep within Earth, in particle accelerators, and in the interactions of cosmic rays with Earth's atmosphere. They stream through the cosmos at nearly the speed of light, carrying information about the most extreme environments in the universe. But they barely notice that matter exists. A neutrino could pass through a wall of solid lead stretching from Earth to the nearest star without hitting a single atom. The universe is essentially transparent to them. This elusiveness stems from the nature of the weak nuclear force, one of the 4 fundamental interactions in nature. The weak force is responsible for radioactive decay and certain nuclear reactions. Unlike electromagnetism, which acts over infinite distances, or the strong force, which binds quarks into protons and neutrons with tremendous power, the weak force operates only at subatomic distances. It's mediated by massive particles called W and Z bosons, which are so heavy that they can only be exchanged over tiny ranges. This gives the weak interaction its characteristic properties: short range and feeble strength, compared to electromagnetism or the strong force. Neutrinos interact exclusively through this weak force and through gravity. Gravity, given their minuscule mass, is utterly negligible. This leaves only the weak interaction, which means neutrinos rarely collide with anything. The probability that a neutrino will interact with matter is characterized by something called the cross-section, which you can think of as the effective target size a neutrino presents. For low-energy neutrinos, this cross-section is absurdly small, roughly 10 to the power of -44 square centimeters. To put this in perspective, if you scaled a neutrino up to the size of a basketball, its effective interaction cross-section would be smaller than an atom. Every second, trillions of neutrinos pass through your body. Right now, as you're watching this, neutrinos from the sun are streaming through you at nearly the speed of light. They entered through your head, passed through your brain, your organs, your bones, and emerged from your feet without interacting with a single atom. To a neutrino, solid matter is as transparent as air. Actually more transparent. Air at least scatters light. Neutrinos barely notice that matter exists at all. The history of neutrino physics is a story of theoretical prediction, decades of searching, and persistent detective work. Wolfgang Pauli first proposed the neutrino's existence in 1930, not because anyone had seen one, but because the numbers in radioactive beta decay weren't adding up. When a neutron decays into a proton and an electron, energy and momentum seem to disappear. Conservation laws, the bedrock principles of physics, appeared to be violated. Rather than abandon conservation, Pauli suggested that an invisible, barely interacting particle was carrying away the missing energy. He called it the neutrino, Italian for little neutral one. For 26 years, the neutrino remained purely theoretical. Nobody had ever detected one. Many physicists were skeptical it would ever be possible. The cross-section was so small, the interaction so rare, that catching a neutrino seemed like trying to photograph a ghost. But in 1956, Frederick Rains and Clyde Cowan succeeded using a nuclear reactor at the Savannah River site in South Carolina. They positioned massive tanks of water laced with cadmium chloride next to the reactor core. Nuclear reactors produce enormous numbers of electron antineutrinos as byproducts of fission. If even a tiny fraction of these interacted with protons in the water, they would produce a characteristic double flash of light that could be detected. The experiment required extraordinary patience. For months they collected data, sifting through background noise for the telltale signature of neutrino interactions. Finally, they saw it. The unmistakable signal of anti-neutrinos colliding with protons. The neutrino, Pauli's mathematical fiction, was real. Raines would eventually win the Nobel Prize for this achievement, though sadly Cowan had died before the prize was awarded. The discovery opened an entirely new window on the universe, allowing us to peer inside stars and probe the weak nuclear force with unprecedented precision. The Sun produces neutrinos through nuclear fusion reactions in its core. When hydrogen atoms fuse into helium, releasing the energy that makes stars shine, they also produce electron neutrinos as a byproduct. These neutrinos escape the Sun's interior immediately, streaming outward at nearly light speed. Light, by contrast, is scattered countless times by the dense plasma in the Sun's core, taking millions of years to random walk its way from the center to the surface. This means neutrinos give us a real-time window into stellar interiors, showing us what's happening in the nuclear furnace right now, rather than what happened millions of years ago. In the late 1960s, physicist Ray Davis built a neutrino detector in the Home State Gold Mine in South Dakota, using 100,000 gallons of cleaning fluid, perchloroethylene, contained in a massive underground tank. The detector sat a mile beneath the surface to shield it from cosmic rays. When solar neutrinos interacted with chlorine atoms in the fluid, they occasionally transformed chlorine into argon. By periodically flushing the tank and counting the argon atoms, Davis could measure the solar neutrino flux. What he found was puzzling. Only about 1/3 of the expected neutrinos were detected. This became known as the solar neutrino problem, a mystery that would persist for 3 decades. The solution involved one of the most surprising discoveries in particle physics: neutrino oscillation. It turns out that neutrinos come in 3 flavors, associated with the 3 charged leptons: electron neutrinos, muon neutrinos, and tau neutrinos. And as neutrinos travel through space, they can transform from one flavor to another, oscillating between identities in a purely quantum mechanical process. The Sun produces electron neutrinos, but by the time they reach Earth, 2/3 have oscillated into muon and tau neutrinos. Davis's detector was only sensitive to electron neutrinos, so he was missing the others. When researchers built detectors capable of seeing all 3 flavors, they found the full expected flux. The solar neutrino problem was solved, and we learned that neutrinos have mass, albeit very small. The discovery of neutrino oscillation won Takaaki Kajita and Arthur McDonald the 2015 Nobel Prize in Physics. It required mass because massless particles can't change their quantum state in the way oscillation demands. This was revolutionary because the standard model of particle physics originally predicted neutrinos to be massless. The discovery forced revisions to our fundamental understanding of particle physics and raised new questions. How much mass do neutrinos have? Why is it so small? How do they acquire it? Supernovae, the violent explosions of dying stars, produce enormous bursts of neutrinos. When a massive star exhausts its nuclear fuel, the core collapses in less than a second, compressing matter to nuclear density. The implosion releases more energy in neutrinos than the star produced in light over its entire lifetime. In 1987, when a star exploded in the Large Magellanic Cloud, a satellite galaxy 160,000 light-years away, neutrino detectors on Earth caught the signal hours before the light arrived. This wasn't magic, it was physics. Neutrinos escaped the collapsing core immediately, while light took time to fight its way through the expanding debris. The detection of supernova 1987A neutrinos confirmed theoretical models of stellar collapse and proved that neutrinos travel at very nearly the speed of light. Modern neutrino detectors have become increasingly sophisticated. IceCube, buried in the Antarctic ice, uses a cubic kilometer of ice as a detection medium. Instrumented with thousands of optical sensors watching for the faint flashes of light when neutrinos interact. Super Kamiokande in Japan contains 50,000 tons of ultra-pure water surrounded by photomultiplier tubes. These massive experiments detect neutrinos from the Sun, from supernovae, from Earth's atmosphere, and occasionally from distant astrophysical sources like blazars and active galactic nuclei. But the neutrinos ANITA searches for are different beasts entirely. These are ultra-high energy neutrinos carrying millions or billions of times more energy than the ones from the Sun. At these energies, neutrinos become much more likely to interact with matter. Their effective cross-section, the probability that they'll hit something, increases dramatically with energy. This is still small by ordinary standards. You could shoot a beam of ultra-high energy neutrinos through thousands of miles of solid lead, and most would pass through unscathed. But some would hit, and the more matter a neutrino has to traverse, the higher the probability of interaction. Earth's diameter is about 8,000 miles of rock, iron, and molten metal. For an ultra-high energy neutrino to travel through the entire planet, entering on one side and emerging on the other, it would need to avoid hitting anything for the entire journey. The probability of this happening depends on the neutrino's energy and the path it takes through Earth. For energies in the range ANITA detects, the probability drops exponentially with the amount of matter traversed. A neutrino coming straight through the core would almost certainly interact before emerging. The angle matters enormously. Shallow angles, where the neutrino skims through Earth's crust, are more likely to succeed. Steep angles, passing through more matter, are less likely. When physicists calculate the expected rate of ultra-high energy neutrino events that should emerge from Earth and be detected by ANITA, they get numbers far below one event per decade of observation. Yet ANITA saw multiple events in just a few years of flight time. This is the crux of the anomaly. Either the events aren't what they appear to be, or something about our understanding of neutrino physics at these energies is wrong. Several explanations have been proposed. Maybe the particles weren't neutrinos at all, but some unknown type of particle that interacts differently with matter. This would be revolutionary, requiring physics beyond the standard model, but it's at least conceivable. New particles are discovered occasionally. The Higgs boson was found in 2012, fulfilling a decades-old prediction. Perhaps there are other particles we haven't yet catalogued, exotic cousins of neutrinos with different interaction properties. Maybe the detections were two neutrinos that had partially travelled through Earth, emerging at angles that made them look like they'd come from deeper than they actually had. Tau neutrinos are special because when they interact with matter, they can produce tau leptons, which then decay quickly. Under certain conditions, this regeneration process might allow a tau neutrino to travel farther through Earth than other flavours, though the calculations suggest this still can't fully explain the ANITA events. Maybe the radio signals were reflecting off subsurface ice layers in ways the researchers hadn't anticipated, creating the illusion of upward-pointing events. Antarctica's ice is not perfectly uniform. There are layers with different densities, interfaces where ice transitions from snow to firn to solid ice. Radio waves can reflect off these boundaries. The ANITA team had considered this possibility and thought they'd ruled it out based on the signal characteristics, but subsequent research suggested that certain types of subsurface reflections might not produce the telltale signs they were looking for. This explanation is currently considered one of the more plausible. The Sun produces neutrinos through nuclear fusion reactions in its core. When hydrogen atoms fuse into helium, releasing the energy that makes stars shine. They also produce electron neutrinos as a byproduct. These neutrinos escape the Sun's interior immediately, while the light we see took millions of years to random walk its way from the core to the surface. Neutrinos give us a real-time window into stellar interiors. Supernovae, the violent explosions of dying stars, produce enormous bursts of neutrinos. In 1987, when a star exploded in a nearby galaxy called the Large Magellanic Cloud, neutrino detectors on Earth caught the signal hours before the light arrived, because neutrinos travel straight through the star's collapsing core while light takes time to fight its way through the debris. We've only known about neutrinos since 1956, when Frederick Rains and Clyde Cowan detected them for the first time using a nuclear reactor and tanks of water. It took decades of patient observation to catch those first interactions. Since then, we've discovered there are three types, or flavors, of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos, each associated with its corresponding charged particle. We've discovered they have mass, though we still don't know exactly how much. We've discovered they can oscillate, transforming from one flavor to another as they travel, a quantum mechanical process that revolutionized our understanding of particle physics and won the 2015 Nobel Prize. But the neutrinos ANITA searches for a different beast entirely. These are ultra-high energy neutrinos carrying millions or billions of times more energy than the ones from the Sun. At these energies, neutrinos become much more likely to interact with matter. Their effective cross-section, the probability that they'll hit something, increases dramatically. This is still small by ordinary standards, You could shoot a beam of ultra-high energy neutrinos through thousands of miles of solid lead, and most would pass through unscathed. But some would hit. Earth's diameter is about 8,000 miles. For a neutrino to traverse the entire planet, entering on one side and emerging on the other, it would have to pass through all that rock and iron and molten metal without interacting. At ultra-high energies, the probability of this happening is vanishingly small. You could observe for millions of years and never see it happen once. This is why the ANITA detections were so shocking. They appear to show exactly this impossible feat occurring not just once but twice. Several explanations have been proposed. Maybe the particles weren't neutrinos at all, but some unknown type of particle that interacts differently with matter. This would be revolutionary, requiring physics beyond the standard model, but it's at least conceivable. Maybe the detections were two neutrinos that had partially travelled through Earth, emerging at angles that made them look like they'd come from deeper than they actually had. This requires some careful geometry and special circumstances, but it's possible. Maybe the radio signals were reflecting off subsurface ice layers in ways the researchers hadn't anticipated, creating the illusion of upward-pointing events. This is currently considered one of the more likely explanations. Or maybe, just maybe, there's something genuinely weird going on that we don't yet understand. Not a parallel universe, but perhaps some subtle aspect of neutrino physics that we've missed. New physics at ultra-high energies, an interaction process we haven't accounted for. This is what makes the ANITA anomalies scientifically interesting even if they don't point to mirror realities. They represent a genuine puzzle, a piece of data that doesn't quite fit our models. And puzzles like these, historically, have led to some of the biggest breakthroughs in physics. The follow-up experiment called PUO launched in 2024 with upgraded detectors and improved sensitivity. It's designed to either confirm the anomalies with more data or figure out what went wrong with the original detections. This is how science advances, not through breathless headlines about parallel universes, but through careful observation, rigorous analysis, and the patient accumulation of evidence. The process is slower, less dramatic, but ultimately more reliable than anything splashed across social media. Here's the irony in the whole ANITA debacle. While the specific claim that scientists had detected a parallel universe was false, the concept of parallel universes is actually taken seriously by many physicists. Not as science fiction speculation, not as wild-eyed fantasy, but as genuine theoretical possibilities that emerge from our best understanding of quantum mechanics and cosmology. The multiverse, as it's called in scientific literature, comes in several different flavours, each arising from different branches of physics. The most famous version is probably the many worlds interpretation of quantum mechanics, proposed by Hugh Everett in his 1957 doctoral thesis. Everett was trying to solve one of the deepest puzzles in quantum theory, the measurement problem. In quantum mechanics, particles exist in superpositions, occupying multiple states simultaneously until they're measured. Schrödinger's famous cat thought experiment captures this weirdness. A cat in a box can be both alive and dead at the same time, according to the math, until someone opens the box and observes it. To truly understand what Everett was grappling with, we need to dive deeper into quantum weirdness. Before quantum mechanics, physics was deterministic. Newton's laws told you that if you knew a system's initial conditions precisely, you could predict its future evolution exactly. The universe was like clockwork, wound up at the Big Bang and ticking forward according to mathematical rules. Quantum mechanics shattered this certainty. In the quantum realm, particles don't have definite positions or velocities until measured. Instead, they exist in superpositions of all possible states, described by a mathematical object called a wave function. The wave function evolves deterministically according to the Schrödinger equation, but it doesn't tell you where a particle is. It tells you the probability of finding the particle at different locations if you measure it. Before measurement, the particle genuinely doesn't have a definite position. It's not that we don't know where it is, it's that it isn't anywhere in particular. It's smeared out in a probability cloud. This sounds like philosophical word games until you start doing experiments. In the famous double-slit experiment, you shoot particles like electrons one at a time toward a barrier with two slits. Classical physics says each electron should go through one slit or the other and create a pattern on a detector screen behind the barrier. But that's not what happens. Instead, the electrons create an interference pattern, alternating bands of high and low intensity, exactly like waves passing through both slits simultaneously and interfering with themselves. Each electron, even though it's a particle, behaves as if it went through both slits at once. But here's where it gets truly strange. If you try to observe which slit the electron went through, by placing a detector at the slits, the interference pattern disappears. The act of measurement forces the electron to choose one slit or the other, and it behaves like a classical particle. The measurement collapses the wave function from a superposition of both slits to a definite state of one slit. This collapse is instantaneous and seems to violate the principle that information can't travel faster than light. If you measure an entangled particle here, its partner's state changes instantly, even if it's on the other side of the galaxy. The Copenhagen interpretation, developed by Niels Bohr, Werner Heisenberg, and others in the 1920s and 30s, embraced this weirdness. It said that particles genuinely don't have definite properties until measured. The wave function describes all you can know about a system, and measurement causes a physical collapse that selects one outcome from the range of possibilities. The math works brilliantly, making predictions of astonishing accuracy, but philosophically it's deeply unsatisfying. It treats measurement as a primitive concept, not explained by the theory but added as a separate postulate. What counts as a measurement? Why does observation have this special power? The Copenhagen interpretation doesn't really answer these questions. It just asserts that this is how nature works. Hugh Everett found this intellectually unacceptable. He wondered whether we could take the Schrödinger equation seriously, applying it to everything, including the measuring apparatus and the observer. What if nothing ever collapses? What if the wave function just keeps evolving according to the Schrödinger equation, becoming more and more complex, but never jumping discontinuously from superposition to definite state? Here's what he realized. When a quantum system interacts with a measuring device, they become entangled. The combined system of measured object plus measuring device plus observer enters a superposition. From the outside, from some God's eye view, the wave function describes a superposition of all possible measurement outcomes occurring simultaneously. But from inside the system, each version of the observer sees only one outcome. The superposition hasn't disappeared. It's just that the different terms in the superposition no longer interact. They've decohered, becoming effectively separate branches of reality. Think of it this way. Before you measure Schrödinger's cat, the universe is in a superposition of cat, alive you see alive, plus cat dead you see dead. When you open the box, the wave function doesn't collapse. Instead, you get entangled with the cat. Now there are two versions of you. One who saw a live cat, and one who saw a dead cat. Both are equally real, equally physical. They exist in the same space but in different branches of the universal wave function. Each version of you is convinced they saw a definite outcome. Neither can observe or communicate with the other because they've decohered. The branches have become orthogonal in an abstract mathematical space, unable to interfere. This solves the measurement problem by dissolving it. There's no special moment of collapse, no mysterious discontinuity in the laws of physics. The Schrödinger equation applies everywhere and always. Measurement becomes just another physical interaction, no different in kind from any other. The appearance of definite outcomes arises not because the wave function collapses, but because you, the observer, have split into multiple copies, each experiencing one possible result. But this solution comes at an enormous ontological price. It implies that every quantum event causes the universe to split, and I mean every event. Every time a photon in the sun's core bounces off an electron, the universe splits into branches corresponding to all the different possible scattering angles. Every radioactive decay, every quantum fluctuation in every atom of your body causes branching. The rate of splitting is unimaginably vast, far beyond the trillion per second. The traditional Copenhagen interpretation says that measurement causes the wave function to collapse, forcing the quantum system to choose one state or another. But this raises uncomfortable questions. What counts as a measurement? Why does observation have this magical power to collapse possibilities into realities? Everett proposed a radical alternative. Nothing collapses. When a quantum system evolves into a superposition of multiple states, the entire universe splits into multiple branches, each corresponding to one possible outcome. In one branch, the cat is alive. In another, it's dead. Both branches are equally real, equally physical, equally actual. This sounds insane at first hearing. It implies that every quantum event, and there are countless trillions of them happening every second, causes the universe to split into multiple copies. But Everett and his modern defenders argue that this apparent extravagance is actually a virtue. The theory is mathematically simpler than Copenhagen. It doesn't need to add special rules about measurement or collapse. Everything follows from the Schrödinger equation, applied universally. There's a kind of Occam's razor at work. We multiply entities, yes, creating vast numbers of parallel worlds, but we simplify the laws. Instead of two sets of rules, one for evolution and one for measurement, we have just one rule that applies everywhere. Consider what happens in your brain when you make a decision. Neural activity involves countless quantum events, ion channels opening and closing, neurotransmitters binding to receptors, quantum tunneling and enzyme reactions. Each of these events can go multiple ways. In classical physics, thermal noise ensures some randomness, but quantum mechanics says these processes exist in genuine superpositions until the quantum states decohere. In many worlds, your brain is constantly splitting into branches corresponding to different patterns of neural firing. Most of these differences are too subtle to notice consciously, but occasionally a decision truly hangs in the balance, and the different branches lead to macroscopically different outcomes. So there are branches where you took that job offer, and branches where you declined. Branches where you spoke up in the meeting, and branches where you stayed silent. The version of you in each branch feels like they made a choice, experiencing it as a single definite action. But from the God's eye view of the universal wave function, all the possibilities played out. Your existence is fractured into uncountable copies spread across the branching multiverse. This seems to undermine the significance of choice and the moral weight of decisions. If all possibilities are realized, what does it matter which branch you find yourself in? Philosophers have debated this intensely. Some, like David Deutsch, argue that you should think of your decisions as determining the measure or weight of different outcomes. Good choices increase the quantum amplitude of favourable branches. Bad choices increase the amplitude of unfavourable ones. You're not choosing between all or nothing outcomes, but distributing probability weight across possibilities. This preserves moral responsibility in a branching universe. Others object that this makes ethics intolerably strange. If murder happens in some branches no matter what you do, does that diminish the wrongness of choosing to murder in this branch? The many worlds defender might respond that each branch has its own moral reality. The version of you in the murder branch has committed an act with consequences that the non-murder branch versions haven't. Your choice determines which version of you exists in which type of branch, and that matters enormously to the people affected in each branch. The probability question has been particularly vexing. Standard quantum mechanics makes probabilistic predictions. We can say an electron has a 30% chance of being spin up and a 70% chance of being spin down when measured. In many worlds, both outcomes happen, so where do these percentages come from? In one approach, developed by David Deutsch, Simon Saunders, David Wallace, and others, probability emerges from decision theory. If you're a rational agent trying to maximize expected value across branches, you should assign credences to outcomes proportional to the quantum amplitude squared, which recovers the Born rule, the standard formula for quantum probabilities. This derivation is controversial. Critics argue it's circular, smuggling in the Born rule through the back door rather than deriving it from first principles. Defenders insist it's valid, showing that rational behavior in a branching multiverse naturally leads to treating quantum amplitudes as probabilities. The debate continues, technical and heated, in philosophy journals and Quantum Foundation's conferences. This sounds insane at first hearing. It implies that every quantum event, and there are countless trillions of them happening every second, causes the universe to split into multiple copies. It means that there are unimaginably vast numbers of parallel realities, each differing by the outcomes of quantum measurements. It means that every choice you've ever made, every decision, every quantum fluctuation in your brain, has spawned branches where different choices were made. There's a branch where you took that job you turned down, a branch where you said yes instead of no, a branch where you were never born at all because a crucial quantum event in your parents' history went differently. And yet, for all its apparent extravagance, the many worlds interpretation is considered a legitimate mainstream approach to quantum mechanics. Why? Because it's mathematically coherent and arguably simpler than the alternatives. It takes the Schrödinger equation, the fundamental equation governing quantum systems, at face value. It doesn't require adding extra postulates about wave function collapse or special rules for measurements. Everything follows from quantum mechanics applied universally, without exceptions. The physicist David Deutsch, one of the founders of quantum computing, has argued passionately for many worlds. He points out that quantum computers themselves provide indirect evidence for the multiverse. A quantum computer with just 300 qubits can exist in a superposition of more states than there are particles in the observable universe. Where do these computations happen? If you take quantum mechanics seriously, Deutsch argues, they're happening in parallel universes. The quantum computer is effectively borrowing computational resources from vast numbers of parallel realities, all working on the same problem simultaneously. Critics of many worlds raise valid objections. If we split every instant into countless branches, why don't we experience this? Why do we only perceive one history, one timeline? The answer has to do with decoherence, the process by which quantum superpositions become effectively classical through interaction with their environment. Once you're part of one branch, you can't communicate with or observe the others. They become, for all practical purposes, separate universes. You might exist in countless copies across the multiverse, but each copy is completely isolated from all the others, unable to know they exist. Another concern is probability. Quantum mechanics makes probabilistic predictions. We can say that a particle has a 30% chance of being here and a 70% chance of being there. In many worlds, both outcomes happen. So where do the probabilities come from? This has been a subject of intense debate. Some researchers argue that probability in many worlds should be understood as a measure of the weight or thickness of different branches. Outcomes with higher quantum amplitude correspond to branches with more of you in them, in some abstract sense. It's weird, and not everyone finds this satisfying, but serious work has been done to show that the familiar probabilistic predictions of quantum mechanics can emerge from many worlds if you think carefully about what probability means in a branching multiverse. The key point here is that many worlds is not about parallel universes in some distant part of space. These aren't separate regions of the cosmos that we might someday visit. They're parallel quantum realities, coexisting in the same space but separated by quantum decoherence. If many worlds is correct, there are versions of you right here, right now, occupying the same location, but in different quantum branches. You can never meet them, never communicate with them, never know they exist. They're as unreachable as if they were infinitely far away. This is very different from the kind of parallel universe the ANITA story suggested. The viral headlines implied a mirror universe that could somehow interact with ours, sending particles across the boundary. That's not how many worlds works. The branches don't communicate. There's no mechanism for particles to cross between them. So even if you accept many worlds, even if you believe in quantum parallel universes, it doesn't help explain anomalous neutrino detections. But many worlds isn't the only type of multiverse in serious scientific discussion. There are others, each arising from different areas of physics, each with its own implications and challenges. To understand the full landscape of parallel universe theories, we need to explore cosmic inflation and what happens when space itself splits into multiple domains. In the early 1980s, physicists realized that standard Big Bang cosmology had some serious problems. The universe appeared to be remarkably uniform on large scales. The cosmic microwave background radiation, the afterglow of the Big Bang, has almost exactly the same temperature in every direction we look, differing by only about 1 part in 100,000. This is weird because regions of the universe that are now on opposite sides of the observable cosmos have never been in causal contact. Light hasn't had time to travel between them since the Big Bang. So how did they end up at the same temperature? It's like finding two people on opposite sides of Earth wearing identical outfits without ever having communicated. The universe is also remarkably flat. The geometry of space on cosmic scales is very close to Euclidean, the flat geometry you learned in high school, but there's no reason it had to turn out this way. The universe could have been curved, either positively like a sphere or negatively like a saddle. The fact that it's almost perfectly flat requires the initial conditions to be fine-tuned to extraordinary precision. It's as if someone carefully adjusted the settings of the universe at the Big Bang to create exactly the flatness we observe. Alan Guth, Andrei Linde, and others proposed a solution called cosmic inflation. In the first tiny fraction of a second after the Big Bang, perhaps around 10 to the power of negative 35 seconds, space underwent a period of exponential expansion. A region smaller than a proton inflated to the size of a basketball, or larger in an unimaginably short time. This rapid expansion smoothed out any initial irregularities and flattened the geometry of space, solving both the uniformity problem and the flatness problem in one stroke. The mechanism driving inflation is a hypothetical scalar field called the inflaton. Think of it as a kind of energy field permeating all of space, similar to the Higgs field that gives particles mass. When the inflaton field sits at a high energy value, it creates a negative pressure, a repulsive gravitational effect that causes space to expand exponentially. This is counterintuitive because we normally think of gravity as attractive. But Einstein's equations allow for repulsive gravity when you have the right kind of energy density. The vacuum itself, when charged with inflaton energy, pushes space apart. As the inflaton field rolls down its energy curve toward lower values, the expansion accelerates. Space stretches faster than light, doubling in size every tiny fraction of a second. After perhaps 10 to the power of negative 32 seconds, the inflaton field reaches the bottom of its energy curve. Inflation stops. The field's energy converts into a hot plasma of ordinary particles. The universe reheats, and from that point on, it expands according to standard Big Bang cosmology. The brief inflationary period has set the stage for everything that follows. Inflation has been spectacularly successful at explaining observations. The cosmic microwave background, that faint glow of ancient light filling the universe, shows tiny temperature fluctuations with exactly the pattern inflation predicts. These fluctuations arose from quantum jitters in the inflaton field, microscopic variations that got stretched to cosmic scales by inflation. They seeded the formation of galaxies and large-scale structure. The match between theory and observation is remarkably precise. Most cosmologists now accept that something like inflation probably happened. But inflation comes with an unexpected consequence. It might be eternal. The key insight came from Paul Steinhardt and Alexander Vilenkin in the early 1980s. They realized that quantum mechanics makes the inflaton field fluctuate. In most regions of space, the field rolls downhill, inflation ends, and you get a normal universe like ours. But in some regions, quantum fluctuations push the field back uphill to higher energy values. In those regions, inflation continues, and because inflating space expands exponentially, the regions that keep inflating quickly dominate the total volume. Picture it like this. You have an inflating space filled with inflaton field energy. Quantum fluctuations create variations. Most patches of space exit inflation and become bubble universes filled with matter and radiation. But a few patches get lucky. Their inflaton value fluctuates upward, and they keep inflating. Those patches grow exponentially, becoming vastly larger than the bubbles that stopped inflating. Within each still inflating patch, the process repeats. More bubbles form, surrounded by more inflating space. It's a fractal structure, bubbles within bubbles within bubbles, with no end. Once eternal inflation starts, it never completely stops. Oh, it stops in our bubble. The inflaton field here rolled down to zero, inflation ended, the universe reheated, and we got stars and galaxies and planets. But outside our bubble, beyond our observable horizon, inflation continues, and it creates more bubbles, which themselves are surrounded by eternally inflating space. The process goes on forever into the future. Each bubble becomes its own universe, its own vast expanse potentially containing trillions of galaxies spread across billions of light years. This is the inflationary multiverse. If eternal inflation is correct, our observable universe is just one bubble among infinitely many. We're living inside a finite island of normal space-time, surrounded by an ocean of still inflating space that we can never reach or observe. The bubbles are separated by exponentially expanding barriers. Even if you could travel at the speed of light, you could never reach another bubble, because the space between is stretching faster than you can cross it. And here's where it gets even stranger. The physics inside each bubble might be different. This happens because of symmetry breaking, a process fundamental to particle physics and cosmology. At extremely high energies, the laws of physics are symmetric and unified. All the forces, electromagnetic, weak, strong, maybe even gravity, are different aspects of a single unified interaction. As energy decreases, these symmetries break, like water freezing into ice crystals with particular orientations. The forces separate, particles acquire masses, and the specific properties of physics emerge. But symmetry breaking involves random chance. It's like dropping a pencil balanced on its tip. It will fall in some direction, but which direction is random? Similarly, when a bubble universe forms and the inflaton field decays, the symmetries can break in different ways in different bubbles. One bubble might end up with electromagnetic and weak forces that differ in strength from ours. Another might have a different mass for the electron, or a different strength of the strong nuclear force. Some bubbles might even end up with different numbers of spatial dimensions as certain dimensions remain curled up while others expand. The possible variations are constrained by the underlying theory. You can't have arbitrary physics. Everything still follows from the same fundamental equations. But those equations admit multiple solutions, multiple vacuum states, each with different low-energy properties. In string theory, this multiplicity is called the landscape. String theory attempts to unify all forces, including gravity, by describing particles as tiny vibrating strings in 10 or 11 dimensions. The extra dimensions must curl up into small structures called Calabi-Yau manifolds. But there are many possible geometries for these manifolds, perhaps 10 to the power of 500 different configurations. Each Calabi-Yau geometry produces different physics in the remaining 4 dimensions of space-time, different particle masses, different force strengths, different values for fundamental constants. Early string theorists hoped there would be a unique solution, one special geometry that nature preferred. Instead, they found a vast landscape of possibilities, all seemingly on equal footing. If eternal inflation is real, these possibilities get actualized in different bubble universes. Our bubble sits at one point in the landscape, other bubbles sit at other points. The combination of eternal inflation and the string landscape produces a multiverse of staggering, almost incomprehensible diversity. Some physicists find this appealing because it could explain apparent fine-tuning. Our universe's properties seem remarkably suited for life. Change the strength of gravity by a tiny amount and stars can't form. Change the mass of the electron, and chemistry doesn't work. Change the cosmological constant by much, and space expands too fast for galaxies to coalesce. We appear to live in a narrow habitable zone in the space of possible physical laws. In a single universe, this fine-tuning cries out for explanation. Why are the parameters so precisely balanced? In a multiverse, the question transforms. With infinitely many bubbles exploring the landscape, it's unsurprising that some have the right properties for life. We must find ourselves in one of those rare bubbles because we couldn't exist in the others. It's a selection effect, no different from noticing that Earth has liquid water and breathable atmosphere. Those properties aren't fine-tuned by cosmic design. They're selected by the requirement that we exist to observe them. This anthropic explanation bothers many physicists intensely. It seems to give up on finding deep reasons for why the universe is the way it is. Instead of explaining the electron mass through fundamental principles, we just say it happens to have that value in our bubble. Critics like Paul Steinhardt argue this robs physics of its predictive power. If any observation can be explained by pointing to some bubble somewhere, the theory becomes vacuous, incapable of being tested or falsified. Inflation has been spectacularly successful. Observations of the cosmic microwave background match the predictions of inflationary theory remarkably well. The tiny temperature fluctuations we see in the CMB appear to have exactly the characteristics that inflation predicts, arising from quantum fluctuations stretched to cosmic scales. Most cosmologists now accept that something like inflation probably happened in the early universe. But inflation comes with an unexpected consequence. It might be eternal. Here's how that works. Inflation is driven by a field called the inflaton, a hypothetical quantum field that fills space. When the inflaton field has high energy, it causes space to inflate exponentially. When the energy drops to a lower state, inflation stops, and the energy gets converted into the hot plasma of ordinary particles that we see in the aftermath of the Big Bang. But quantum mechanics tells us that the inflaton field should fluctuate. In some regions, the field drops to a lower energy and inflation ends. In other regions, quantum fluctuations push the field back up to higher energy, and inflation continues. The regions where inflation continues expand exponentially, becoming vastly larger than the regions where it has stopped. This creates a fractal structure. Within the eternally inflating space, bubbles of non-inflating space nucleate and grow. Each bubble becomes its own universe, its own vast region of space filled with galaxies and stars and planets. Our observable universe is just one such bubble. Outside our bubble, inflation continues, and within that inflating region, more bubbles form, each creating more universes. This process has no end. It continues forever into the future, creating an infinite number of bubble universes within an ever-expanding inflating background. This is the inflationary multiverse, and if eternal inflation is correct, it means our universe is just one among infinitely many. Each bubble universe might have different properties. The physics inside each bubble, the laws governing particles and forces, might vary. This happens because of something called symmetry breaking. At high energies, physics is symmetric and unified. As energy drops, symmetries break and forces separate, like water freezing into ice with different crystalline structures. Different bubbles might freeze in different ways, ending up with different particle masses, different force strengths, even different numbers of spatial dimensions. Some physicists find this appealing because it could explain the apparent fine-tuning of our universe. The laws of physics in our cosmos seem remarkably suited for the emergence of complex structures like galaxies, stars, and life. If the strong nuclear force was slightly weaker, atomic nuclei couldn't form. If gravity was slightly stronger, stars would burn out in thousands of years instead of billions. If the cosmological constant were much larger, space would expand so fast that galaxies could never form. Our universe appears to sit in a narrow range of parameters that allow for complexity and life. Let's be more specific about this fine-tuning, because the numbers are genuinely astonishing. Consider the cosmological constant, which governs how fast empty space pushes itself apart. This constant, denoted by the Greek letter lambda, has been measured to be roughly 3 times 10 to the power of negative 122 in natural units. That's a decimal point followed by 121 zeros and then a 3. It's extraordinarily close to 0, but not exactly 0. Particle physics suggests the vacuum energy, which contributes to the cosmological constant, should naturally be around 1 in natural units. The discrepancy is 122 orders of magnitude, making this what physicist Steven Weinberg called the worst theoretical prediction in the history of physics. But here's the remarkable thing. If the cosmological constant were even slightly larger, say 10 to the power of negative 120 instead of 10 to the power of negative 122, the universe would have expanded so rapidly in its early history that matter could never clump together. No galaxies would form, no stars would ignite, no planets would coalesce. The universe would remain a cold, thin gas, spreading ever thinner as space stretched. For structure to emerge, for complexity to arise, for life to develop, the cosmological constant must be small, not 0, interestingly. Current observations show it's actually slightly positive. But small enough that gravity can still pull matter together into interesting configurations. Steven Weinberg used this reasoning in 1987 to make a prediction. If there's a multiverse where the cosmological constant varies between bubbles, and if we're reasoning anthropically, then our universe's value should be around the maximum that still allows galaxies to form. He calculated this threshold and predicted we should observe a cosmological constant no larger than about 10 to the power of negative 121. At the time, the cosmological constant hadn't been measured. Most physicists assumed it was exactly 0. But in 1998, observations of distant supernovae revealed that cosmic expansion is accelerating, driven by what we now call dark energy. The inferred cosmological constant came out to about 3 times 10 to the power of negative 122, remarkably close to Weinberg's anthropic prediction. This is one of the successes of anthropic reasoning in a multiverse framework. The strength of gravity presents another fine-tuning puzzle. Gravity is incredibly weak compared to the other forces. The electromagnetic repulsion between 2 electrons is about 10 to the power of 42 times stronger than their gravitational attraction. This enormous weakness is essential for life. If gravity were much stronger, stars would burn their fuel rapidly, lasting only thousands or millions of years instead of billions. Complex evolution requires stable energy sources operating over long timescales. Weak gravity gives us those long-lived stars. But weak gravity also means stellar nucleosynthesis barely works. Inside stars, hydrogen fuses into helium, releasing energy. This requires overcoming the electromagnetic repulsion between protons. Only the extreme temperatures and pressures in stellar cores make fusion possible. If gravity were weaker, stars couldn't compress matter enough to trigger fusion. If it were much stronger, fusion would be too violent, and stars would explode rather than burn steadily. The strength of gravity sits in a narrow range that allows for stable, long-lived stars capable of creating heavier elements through fusion, while remaining stable for billions of years. The masses of fundamental particles also show apparent fine-tuning. The electron is about 1,036 times lighter than the proton. This ratio determines the size of atoms and the energy of chemical bonds. If the electron were heavier, atoms would be smaller, and the energy scales of chemistry would shift. Too heavy, and electrons might be captured by protons, collapsing matter into something like neutron star material. Complex chemistry requires the electron mass to be in a specific range relative to the proton mass. The difference in mass between the neutron and proton is another critical parameter. The neutron is about 0.1% heavier than the proton. This small difference is why free neutrons decay into protons, electrons, and antineutrinos in about 15 minutes. Inside atomic nuclei, neutrons are stable, but free neutrons aren't. If the neutron were lighter than the proton, hydrogen would be unstable, and the universe would be filled with neutrons instead of protons. No atoms could form. Alternatively, if the neutron were much heavier, neutrons would decay so quickly that nucleosynthesis in the early universe couldn't build up heavier elements. The narrow mass difference between neutron and proton is crucial for both stellar fusion and the stability of matter. The strong nuclear force, which binds quarks into protons and neutrons and binds protons and neutrons into atomic nuclei, also requires fine-tuning. If the strong force were about 2% weaker, deuterium, the heavy isotope of hydrogen, would be unstable. Deuterium is a key intermediate step in stellar fusion chains. Without stable deuterium, stars couldn't fuse hydrogen efficiently, and helium production would fail. The universe would remain mostly hydrogen. If the strong force were about 2% stronger, protons could stick together directly without needing neutrons. All the hydrogen in the universe would have fused into heavier elements in the first moments after the Big Bang, leaving no fuel for stars. Even the number of spatial dimensions appears fine-tuned. We live in 3 dimensions of space, plus 1 of time. But why 3? In 2 spatial dimensions, complex chemistry seems impossible. You can't have crossing nerve fibers or complicated circulatory systems. In 4 or more spatial dimensions, planetary orbits would be unstable. Gravity in higher dimensions falls off faster with distance, making stable solar systems difficult. 3 dimensions appear to be in a sweet spot for complexity and stability. Critics of fine-tuning arguments note that we don't actually know the space of possibilities. Maybe the parameters couldn't have been different. Perhaps they're determined by some deeper theory we haven't discovered yet, and the values we observe are the only ones mathematically consistent. Or maybe our notion of what counts as habitable is too narrow. We assume life requires chemistry similar to ours, but perhaps very different universes could support very different forms of complexity and even consciousness. We're generalizing from a sample size of 1, which is notoriously unreliable. But proponents point out that even if we're uncertain about alternative chemistries, the fine-tuning remains striking. Many parameter changes would produce universes that are not just inhospitable to life but utterly featureless. No stars, no planets, no structure beyond a thin gas or a uniform soup of particles. The fraction of parameter space that produces interesting universes appears to be small. If you plotted all possible combinations of fundamental constants, the region where complexity can emerge seems to occupy a tiny corner. In the inflationary multiverse, this fine-tuning is explained by selection effect. If there are infinitely many universes with different properties, it's not surprising that we find ourselves in one suited for life. We couldn't exist in the others. It's like winning the lottery, improbable for any individual ticket, but guaranteed that someone wins if enough tickets are sold. In a multiverse, our universe's properties are not fine-tuned by design or luck. They're selected by the requirement that we must exist to observe them. This explanation bothers some physicists intensely. Paul Steinhardt, one of the original developers of inflationary theory, has become one of its harshest critics precisely because of the multiverse implications. He argues that if inflation predicts infinitely many universes with all possible properties, then it predicts nothing. Any observation could be accommodated by pointing to some universe somewhere in the multiverse. The theory loses its predictive power and becomes unfalsifiable. If you can't test it, if you can't prove it wrong, is it really science? Others disagree. They point out that even in a multiverse, certain things are more likely than others. The distribution of universes isn't uniform across all possibilities. Some properties should be common, others rare. We can ask, is our universe typical among those that can support observers? If we find that our universe's properties are extremely atypical, even given the selection effect of our existence, that would be evidence against the multiverse. Conversely, if we find that our properties are about what we'd expect from a random draw weighted by observer likelihood, that supports the multiverse hypothesis. Moreover, the multiverse makes testable predictions about things we should or shouldn't see. For example, if our bubble universe collided with another bubble in the distant past, the collision should have left a mark in the cosmic microwave background. Researchers have looked for such signatures, circular patterns that would indicate a cosmic crash. So far, they haven't found any convincing evidence, which places constraints on the collision rate and the history of our particular bubble. This is science in action. The multiverse makes predictions, observations are made, and the theory is refined or constrained by the data. The inflationary multiverse also connects to another theoretical framework that produces multiple universes, string theory. In string theory, the fundamental constituents of reality are not point particles but tiny vibrating strings. These strings can vibrate in different modes, and different vibration patterns correspond to different particles. It's an elegant idea that naturally unifies quantum mechanics and gravity, solving one of the deepest problems in theoretical physics. But string theory requires extra dimensions of space. Not just the 3 dimensions we experience, but 6 or 7 additional dimensions curled up so small that we don't notice them. The precise way these extra dimensions curl up determines the physics in the remaining 3 large dimensions. And here's the problem. There are an astronomically huge number of ways the extra dimensions could be curled up. Different geometries produce different physical laws, different particle masses, different force strengths. The collection of all these possibilities is called the string theory landscape. Early estimates suggested there might be 10 to the power of 500 different stable configurations, each corresponding to a different possible universe. More recent analysis suggests the number might be even larger, or possibly that many of these configurations are unstable and don't actually produce viable universes. But in any case, string theory appears to predict a vast landscape of possibilities, not a unique set of physical laws. In eternal inflation, these different string theory vacua could be realized in different bubble universes. As bubbles nucleate within the inflating space, they might settle into different configurations of the extra dimensions, different points in the string landscape. Our bubble settled into one particular configuration that happens to support life. Other bubbles settled into other configurations, most of which don't allow for stars or galaxies or chemistry. The combination of eternal inflation and the string landscape produces a multiverse of staggering diversity. Critics like Peter Woit and Lee Smolin argue that this amounts to a failure of string theory. If the theory can accommodate any observed physics by appealing to different configurations in the landscape, then it's not making genuine predictions. It's become a framework so flexible that it can't be tested. Proponents counter that this is premature. We're still learning how to extract predictions from the landscape. Maybe there are patterns, constraints, that limit the range of possible physics even within this vast space of solutions. The debate continues, intense and unresolved, touching on fundamental questions about what makes a scientific theory valid. This is the question that separates science from philosophy. The many worlds quantum branches, the bubble universes of eternal inflation, the varied configurations of the string landscape, all these sound like science fiction. But they're taken seriously by physicists because they emerge naturally from well-established theories. The question is whether they're real or just mathematical artifacts, interesting features of our equations that don't correspond to anything in physical reality. One approach is to look for indirect evidence. If quantum computers can solve problems that would require computational resources exceeding anything available in our universe, that suggests they're borrowing from parallel quantum branches, if we find that our universe's properties are exactly what we'd predict from a random draw in a multiverse weighted by observer likelihood that supports the multiverse hypothesis statistically, If we discover signatures in the cosmic microwave background consistent with collisions between bubble universes, that would be smoking gun evidence for the inflationary multiverse. The challenge is that most versions of the multiverse predict the other universes are fundamentally inaccessible. The many worlds branches have decohered and cannot communicate. The bubble universes are separated by inflating space expanding faster than light. We're causally disconnected from them. It's not like distant galaxies that we can't reach practically but could in principle. These other universes are unreachable in principle, blocked not by distance but by the structure of space-time itself. Some physicists argue this makes the multiverse unscientific. If a hypothesis makes no testable predictions, if it can't be falsified by any conceivable observation, then it belongs to philosophy or metaphysics, not physics. Karl Popper's criterion of falsifiability, the idea that scientific theories must be disprovable, seems to rule out the multiverse from the domain of science. You can never prove the other universes don't exist because you can never look everywhere. The multiverse becomes an unfalsifiable claim, like the existence of invisible unicorns that leave no trace of their presence. But other philosophers of science argue that Popper's criterion is too restrictive. Science doesn't work purely through falsification. Theories are evaluated on multiple grounds: their explanatory power, their mathematical elegance, their ability to unify disparate phenomena, their track record of successful predictions in the domains where they can be tested. By these criteria, the multiverse does reasonably well. It explains apparent fine-tuning without invoking design. It emerges naturally from well-tested theories like quantum mechanics and inflation. It makes some testable predictions, even if not about the other universes directly. Consider an analogy. We believe in quarks even though we've never seen one in isolation and never will, because quarks are permanently confined inside composite particles like protons and neutrons. But the quark model explains an enormous amount of data about particle physics. It makes precise predictions about scattering experiments, decay rates, particle masses. The success of these predictions gives us confidence that quarks are real, even though we can't observe them directly. Similarly, the multiverse might be real, even though we can't observe the other universes directly, if the framework that predicts it keeps making successful predictions in the domains we can test. The most promising avenue for testing the multiverse involves looking at the statistical properties of our universe. If there's only one universe, we have to explain why its properties are what they are. If there are many universes, we can ask whether our properties are typical or atypical among those that could support observers. This turns cosmology into a kind of statistical inference problem. We're trying to deduce the properties of a larger population from a single sample. Steven Weinberg demonstrated this approach in 1987 with a famous calculation involving the cosmological constant. This constant, which governs the acceleration of cosmic expansion, has a value that seems absurdly fine-tuned. Particle physics suggests it should be 120 orders of magnitude larger than what we observe. If it were, space would expand so fast that structures could never form. Weinberg used anthropic reasoning to predict the maximum value the constant could have while still allowing galaxy formation. His prediction, made before the cosmological constant was measured, turned out to be remarkably close to the observed value. This is evidence that anthropic reasoning in a multiverse can make testable predictions. More recent work has explored other statistical predictions. Are there limits on the strength of the weak nuclear force? On the mass of the electron? Researchers can calculate what ranges of these parameters would allow chemistry complex enough for life. Then ask whether our observed values are typical within those ranges. If they're all clustered suspiciously at the edge of what's allowed, that might argue against the multiverse. If they're scattered roughly as expected, that supports it. The experimental signature some physicists are most excited about involves bubble collisions. If our universe is a bubble within an eternally inflating space, and if another bubble formed close enough to ours that we collided before inflation separated us completely, the collision should have left a mark. The impact would create a kind of shock wave propagating through our bubble, producing a circular pattern in the cosmic microwave background. The pattern would be subtle, but potentially detectable with current or near-future telescopes. Imagine two bubbles nucleating in an inflating background. Each bubble expands at the speed of light, while the space between them inflates exponentially. If the bubbles form far apart, they never meet. Inflation drives them apart faster than they can approach. But if they nucleate close enough, they collide. The collision surface forms a disk where the two bubbles meet. propagating through each bubble at light speed. Behind the collision surface, the physics of the two bubbles interact, potentially creating unusual conditions. From our perspective inside our bubble, a collision that happened in the distant past would appear as a circular disk in the sky, like a cosmic bullseye. The collision would have modified the density of matter slightly in that direction, creating an imprint in the cosmic microwave background. Researchers can search for such patterns by analysing CMB data, looking for circular symmetries that stand out from the statistical noise. Several groups have conducted these searches using data from the Planck satellite and earlier missions. They found some interesting candidates, circular features that could possibly be collision signatures. But statistical analysis shows these features are consistent with random chance. When you look at a map with millions of pixels, you'll find some patterns just by accident. None of the candidates are significant enough to claim a detection. The search continues with increasingly sophisticated analysis techniques and better data. The absence of clear collision signatures actually provides information. It constrains the rate at which bubbles nucleate and collide in the eternal inflation scenario. If collisions were very common, we'd expect to see multiple signatures. The lack of detection suggests that either collisions are rare, or our bubble is young enough that we haven't been hit yet, or the signatures are too subtle for current instruments, or eternal inflation isn't happening. Future missions with more sensitive detectors might reveal clearer evidence or tighten the constraints further. Another experimental approach involves quantum systems. If many worlds is correct, the different branches must still be part of one universal wave function, at least in principle. While decoherence makes the branches effectively separate for all practical purposes, perhaps extremely delicate quantum interference experiments could detect subtle effects that hint at the branching structure. Some researchers have proposed experiments with macroscopic quantum superpositions, placing objects large enough to see with the naked eye into quantum superpositions and looking for deviations from standard predictions. The challenge is that decoherence is incredibly efficient. The moment a quantum system interacts with its environment, even slightly, the different branches of the superposition lose their ability to interfere. For macroscopic objects, decoherence happens almost instantaneously. Creating and maintaining a superposition of something as large as a virus or a grain of dust, let alone anything bigger, requires isolation from the environment to an extraordinary degree. Current technology is nowhere near capable of this, but perhaps future advances will make it possible. Quantum computing provides indirect evidence relevant to many worlds. A quantum computer with just 300 qubits can exist in a superposition of 2 to the power of 300 different states simultaneously. This is more states than there are particles in the observable universe. Where is this computation happening? If you take quantum mechanics seriously, and if many worlds is right, it's happening across parallel branches of the wave function, each exploring different computational paths. The quantum computer is essentially borrowing computing resources from the multiverse. David Deutsch makes this argument forcefully. He points out that quantum computers don't just factor large numbers faster than classical computers, they do it in a way that seems to require vastly more computational steps than our universe contains particles. The only sensible explanation, he argues, is that the computation is distributed across parallel realities. Of course, critics of many worlds have alternative explanations involving pilot waves or other interpretations, but the quantum computing argument provides at least circumstantial support for branching. Researchers have looked for such patterns in the data from the Planck satellite, which mapped the CMB with unprecedented precision. They found some interesting candidates, circular features that could possibly be collision signatures, but none are statistically significant enough to claim a discovery. The search continues. Future observations with better sensitivity might reveal clearer evidence or rule out certain models of bubble nucleation and collision rates. Another approach involves quantum gravity experiments. If many worlds is correct, then at some level the different branches must interact through quantum interference effects. These effects would be unimaginably tiny for macroscopic objects, but perhaps detectable in carefully controlled quantum systems. Some researchers have proposed experiments involving superpositions of massive objects, testing whether the interference patterns show deviations from standard quantum mechanics that could hint at many worlds' dynamics. The philosophical debate about the multiverse's scientific status continues. Some argue we should expand our notion of what counts as science to include theories about unobservable entities if those theories are sufficiently well motivated and explanatory. Others insist on maintaining strict empirical standards, rejecting any hypothesis that can't be tested observationally. The tension reflects deeper questions about the goals of science. Are we trying to describe only what we can measure, or are we trying to understand reality as it actually is, even if parts of that reality are forever beyond our observational reach? If parallel universes are real, what does that mean for our understanding of existence? The implications are profound and unsettling. Start with the many worlds interpretation. If every quantum event spawns branches where all possible outcomes occur, then your life has been replaying in variations across countless parallel realities. Every choice you've made, you've also not made in some other branch. Every decision that seemed momentous, where you agonized over the possibilities, played out in all the ways you considered. There are branches where you took that risk, branches where you played it safe, branches where you were never born because some quantum fluctuation in the distant past went differently. This seems to undermine the significance of choice and the weight of moral responsibility. If all possibilities are realized somewhere in the quantum multiverse, does it matter which branch you find yourself in? Philosophers have grappled with this question extensively, and the answers reveal deep tensions in how we think about personal identity, free will, and the meaning of our actions. Some argue that many worlds actually makes your choices more meaningful, not less. Consider your subjective experience. From your first-person perspective, you experience only one history, one sequence of events, one timeline. The version of you in this branch lives with the consequences of the choices made here. The fact that other versions in other branches made different choices doesn't diminish the reality of your experience or the impact of your decisions on the people and world around you in this branch. You still have to decide what to do, and that decision shapes the future of your branch, affecting yourself and everyone else in it. If you choose kindly, you create a branch where kindness happened. If you choose cruelly, you create a branch where cruelty happened. The people affected by your choice experience real consequences. The suffering or joy you cause is no less real because other versions of you in other branches made different choices. From this perspective, moral responsibility remains intact. You're accountable for what happens in your branch, regardless of what happens elsewhere in the multiverse. But others find this cold comfort, arguing that it transforms the nature of personal identity in troubling ways. If there are countless copies of you spread across quantum branches, which one is really you? The traditional view of personal identity assumes continuity. You're the same person who woke up yesterday, who graduated high school years ago, who was born decades ago. But in many worlds, you're constantly splitting. The person who started reading this sentence is not quite the same as the person finishing it. Quantum events during those seconds have created branches where slightly different versions exist. This raises the question of what connects these branches. What makes all these versions count as you? They share a common past up to the point of branching, but thereafter they diverge, accumulating different experiences, different memories, different personality changes based on different events. Given enough time, branches could diverge so dramatically that the versions of you in them share almost nothing in common except ancestral history. Are they still you in any meaningful sense? David Deutsch and others who defend many worlds argue that we should think of ourselves as distributed across many branches, with our decisions steering the probability current, the quantum amplitude, towards some futures rather than others. By making good choices, you increase the measure of good outcomes in the branches where versions of you exist. This preserves moral responsibility and meaningful choice even in a branching multiverse. But it requires accepting a strange, attenuated sense of personal identity, where you're not a single individual but a multiplicity spread across quantum branches, a kind of wave function yourself. The puzzle deepens when you consider quantum immortality, a disturbing thought experiment that follows from many worlds. Imagine a game of Russian roulette implemented with quantum mechanics. A gun connected to a quantum random number generator. If the quantum measurement gives one result, the gun fires. If it gives the other result, it clicks harmlessly. You play this game repeatedly. In the Copenhagen interpretation, you have a chance of dying, and eventually you will. But in many worlds, there's always a branch where the gun doesn't fire. From your subjective perspective, you can only observe branches where you survive. No matter how many times you play, you always find yourself in a branch where you're still alive. Dead versions of you stop observing, so from your first-person perspective, you seem immortal. This doesn't mean you're actually immortal in any useful sense. In the vast majority of branches weighted by quantum amplitude, you die quickly. Most versions of you stop existing, but the few surviving versions keep experiencing, and each always finds itself in a survival branch. The thought experiment reveals how many worlds creates observer selection effects, where what you experience is conditioned on your ability to experience anything at all. Applied to natural aging and death, quantum immortality suggests that there might always be branches where you survive, where the quantum events that would have killed you went differently. Of course, these branches become increasingly improbable as you age. The measure of surviving branches shrinks exponentially, and even in those branches, you'd continue experiencing aging, disease, and deterioration. But the philosophical implication is unsettling. From your subjective perspective, death might be impossible to experience because the very condition of experiencing requires being in a branch where you're alive. Most physicists who support many worlds dismiss quantum immortality as a misapplication of the interpretation. The measure of surviving branches matters. Even though you can only observe survival branches, the fact that your measure shrinks dramatically should affect how you reason about probability and make decisions. You shouldn't play quantum Russian roulette just because there's a branch where you survive. The overwhelming measure of branches involves your death, and rational decision-making should reflect that. The inflationary multiverse raises different philosophical issues, less focused on personal identity and more on cosmic purpose and the nature of physical law. If there are infinitely many bubble universes, each with different physical laws, then somewhere in the multiverse, almost anything that's physically possible happens. There are bubbles where the constants are slightly different and stars burn faster. Bubbles where chemistry works differently, and life takes bizarre forms. Bubbles where conscious observers evolved and are contemplating their own fine-tuning puzzles, wondering whether they're alone in the cosmos. But infinity is a strange beast mathematically and philosophically. In an infinite multiverse, not only does everything possible happen somewhere, it happens infinitely many times. There are infinitely many copies of you having exactly the same thoughts and experiences right now. Infinitely many near copies, differing in tiny details, wearing a different shirt, having slightly different memories, making slightly different choices. This leads to what's called the measure problem in cosmology, a deep mathematical puzzle about how to calculate probabilities in infinite sets. To see the problem, imagine you want to know the probability that an observer in the multiverse will measure some particular value for a physical constant. You might try to count the number of bubbles with that value and divide by the total number of bubbles. But both numbers are infinite. Infinity divided by infinity is undefined, or rather, it can equal anything depending on how you set up the calculation. You need a way to compare infinite sets that differ in size or density, a measure that tells you which infinity is bigger. Different methods of comparison give different answers, and there's no obvious physical principle to choose between them. Some cosmologists argue we should weight bubbles by their volume. But volume is tricky because space is expanding. How do you compare the volumes of regions at different times? Others say we should weight by the number of observers in each bubble. But how do you count observers in a universe where consciousness might be substrate independent, potentially existing in substrates we haven't imagined? Still others propose more exotic weighting schemes based on quantum mechanics or the causal structure of space-time. The choice of measure affects predictions. Depending on your measure, you get different answers about what an observer in the multiverse should typically see. Without solving the measure problem, the multiverse can't make precise quantitative predictions, which weakens its scientific standing and leaves it in a philosophically uncomfortable middle ground between rigorous theory and speculative framework. The inflationary multiverse raises different philosophical issues. If there are infinitely many bubble universes, each with different physical laws, then somewhere in the multiverse, almost anything can happen. There are bubbles where the constants are slightly different and stars burn faster. Bubbles where chemistry works differently and life takes bizarre forms. Bubbles where conscious observers evolved and are contemplating their own fine-tuning puzzles. But infinity is a strange beast. In an infinite multiverse, not only does everything possible happen somewhere, it happens infinitely many times. There are infinitely many copies of you, having exactly the same thoughts and experiences. Infinitely many near copies, differing in tiny details. This leads to what's called the measure problem in cosmology. When you try to calculate probabilities in an infinite multiverse, you run into mathematical difficulties because infinities don't play nicely with probability. To see the problem, imagine you want to know the probability that an observer in the multiverse will measure some particular value for a physical constant. You might try to count the number of bubbles with that value and divide by the total number of bubbles. But both numbers are infinite. Infinity divided by infinity is undefined. You need a way to compare infinite sets that differ in size or density. Different methods of comparison give different answers, and there's no obvious physical principle to choose between them. This measure problem has spawned a small industry of research. Some cosmologists argue we should weight bubbles by their volume. Others say we should weight by the number of observers in each bubble. Still others propose more exotic weighting schemes based on quantum mechanics or the causal structure of space-time. The choice affects predictions. Depending on your measure, you get different answers about what an observer in the multiverse should typically see. Without solving the measure problem, the multiverse can't make precise quantitative predictions, which weakens its scientific standing. The multiverse also challenges our intuitions about uniqueness and contingency. In a single universe, the laws of physics are given, fundamental, the bedrock upon which everything else is built. They might have been different, we might imagine, but in fact they are what they are, and we explain other things in terms of them. In a multiverse, the laws are environmental, variable across different regions or bubbles. They're not fundamental but emergent frozen accidents of symmetry breaking. What seemed like deep truths about reality turn out to be local bylaws, applicable only in our cosmic neighborhood. This can feel disorienting. It undermines a certain kind of reductionist ambition in physics. The dream of finding a theory of everything, a single elegant equation from which all of nature's complexity flows, becomes less compelling if the equation describes not our universe, but a vast landscape of possible universes. We're left explaining our observations by saying we happen to live in this particular bubble, not because the universe had to be this way, but because this is one of the bubbles where observers could exist to notice. Some scientists find this aesthetically displeasing. It feels like giving up on explanation, like invoking a multiverse to avoid the hard work of figuring out why our universe is the way it is. Others see it as liberating. It means we don't have to contort our theories to explain every detail of our observations. Some features might just be accidents, random draws from a vast space of possibilities. This frees up theoretical physics to focus on the features that really are universal, that hold across all bubbles, rather than trying to explain environmental variables. Where does this leave us? We have theoretical frameworks from quantum mechanics and cosmology that naturally predict parallel universes. We have unsolved puzzles like fine-tuning that the multiverse could potentially explain. We have a vigorous debate about whether the multiverse can ever be scientifically tested. And we have no conclusive evidence that parallel universes exist. The next decade will likely bring progress on several fronts. Better observations of the cosmic microwave background might reveal collision signatures or other features that test inflationary predictions. Quantum computing experiments might provide indirect evidence for many worlds by demonstrating computational feats that require vast numbers of parallel quantum branches. String theorists might find ways to constrain the landscape, reducing the number of viable universes and making testable predictions about the physics we should observe. On the theoretical side, work continues on the measure problem, trying to find a principled way to calculate probabilities in an infinite multiverse. Progress here could transform the multiverse from a qualitative framework into a quantitative predictive theory. Philosophers of science are refining their understanding of what makes a theory scientific, potentially developing criteria that can accommodate hypotheses about unobservable domains while still maintaining empirical rigor. The search for evidence will continue through programs like the Simons Observatory and next-generation cosmic microwave background experiments. These will map the early universe with unprecedented precision, looking for patterns that match theoretical predictions of inflation, bubble collisions, or other multiverse signatures. Particle accelerators continue pushing to higher energies, searching for hints of physics beyond the standard model that might connect to the string landscape or other multiverse frameworks. But we may also have to accept the possibility that the multiverse question cannot be definitively answered with current or foreseeable technology. The other universes might be genuinely, permanently inaccessible to observation. In that case, belief in the multiverse becomes a matter of theoretical judgment rather than empirical proof. We assess it the way we assess any hypothesis about the unobservable, by its explanatory power, its theoretical economy, its connection to well-tested theories, its ability to illuminate and unify our understanding. Science has always involved inferences about things we can't directly see. We believe in atoms and quarks and black holes based on indirect evidence and theoretical reasoning. The multiverse might be no different, just more extreme, or it might genuinely lie beyond the reach of science, a question for metaphysics rather than physics. Time and further research will tell. Let's summarize where we stand. The viral story about scientists discovering a parallel universe was false. The ANITA experiment detected anomalous neutrino-like events that remain unexplained, but the most likely explanations involve mundane physics like radio reflections, not revolutionary discoveries about the nature of reality. The suggestion that these events came from a mirror universe with backward time was one theoretical speculation among many, not a confirmed finding. But the broader scientific investigation of parallel universes is alive and well. The many worlds interpretation of quantum mechanics, while controversial, is a mainstream approach taken seriously by many physicists. It predicts vast numbers of quantum branches splitting every instant, each equally real. The inflationary multiverse, arising from cosmic inflation combined with string theory or other frameworks, predicts vast numbers of bubble universes with varying physical properties. These are not fringe ideas, but active areas of research. The evidence for parallel universes is indirect and theoretical rather than observational. We have no photographs of other realities, no messages from parallel versions of ourselves. What we have are equations that seem to predict their existence, puzzles about fine-tuning that they could explain, and ongoing debates about whether they can be scientifically tested. Some researchers are optimistic that signatures might eventually be found in cosmological observations or quantum experiments. Others are skeptical, arguing that the multiverse will forever remain beyond empirical reach. What matters is maintaining intellectual honesty about what we know and what we're speculating about. The universe is stranger than common sense suggests. Quantum mechanics, general relativity, cosmological observations all point to a reality far more bizarre than the everyday world of our experience. Parallel universes, whether quantum branches or cosmic bubbles, might be part of that strangeness, or they might be mathematical artifacts that don't correspond to physical reality. The proper scientific attitude is open-minded skepticism. We take the theoretical arguments seriously because they arise from well-tested physics. We look for evidence because that's how we move from speculation to knowledge. We acknowledge uncertainty because that's honest, and we push back against sensational claims because accuracy matters more than clicks. The ANITA story is a cautionary tale about how science gets communicated. A legitimate scientific puzzle got transformed into a false discovery through a chain of simplifications, exaggerations, and misunderstandings. Theoretical speculation became reported as fact. Qualifications and uncertainties disappeared. And the public was left with the impression that something revolutionary had been confirmed when in fact it hadn't. This matters beyond just this one story. Science communication is hard. Real research is tentative, provisional, hedged with caveats. Headlines demand certainty. Social media rewards sensationalism. The incentives push toward overhyping findings, presenting speculation as settled fact, turning maybes into definites. Researchers who speak carefully get ignored in favor of those willing to make bold claims. This corrodes public trust and creates an environment where people can't tell genuine discoveries from misreported speculation. We need better science literacy, but we also need better science communication. Journalists should resist the temptation to simplify away nuance. Social media platforms should think carefully about how their algorithms promote content. Scientists should engage with public communication, not leaving it to those who might get the details wrong. And all of us should cultivate healthy skepticism, checking sources, reading beyond headlines, asking whether a claim sounds too sensational to be true. The parallel universe you may have heard about from the viral stories, the one supposedly detected in Antarctica where time runs backward, doesn't exist, or at least we have no evidence that it does. The ANITA experiment found something puzzling, and physicists proposed various explanations, but none have been confirmed. The media transformed speculation into certainty, and a scientific mystery became a false discovery in the public imagination. This story matters beyond just correcting one misunderstanding. It illuminates fundamental issues in how we know what we know, how information flows from research labs to the public, how truth gets distorted through communication channels, optimized for engagement rather than accuracy. Every day, we're bombarded with claims about scientific discoveries, technological breakthroughs, medical miracles. How do we distinguish genuine advances from hype, solid findings from speculation, careful science from sensationalism? The answer requires scientific literacy, but not in the sense of memorizing facts from textbooks. What we need is epistemic literacy, understanding how knowledge is produced, how certainty is established, what counts as evidence, how scientists think about uncertainty and probability. This means learning to recognize hedging language in research papers, understanding the difference between correlation and causation, knowing what statistical significance means and what it doesn't mean, appreciating the role of replication and peer review. It also requires media literacy, recognizing clickbait, checking sources, reading beyond headlines, understanding the incentive structures that shape journalism and content creation. When you see a headline claiming scientists have discovered something revolutionary, ask questions. Who are these scientists? What institution are they from? Where was the research published? Was it peer-reviewed? What do other experts in the field say? Are there alternative explanations? How certain are the findings? These questions seem tedious when you just want to know whether the exciting claim is true, but they're essential bulwarks against misinformation. The internet has democratized access to information, which is wonderful. But it's also enabled the rapid spread of false information, and the algorithms that govern social media amplify whatever generates engagement, regardless of truth. Sensational falsehoods often spread faster and farther than careful truths. Building resistance to this requires active effort and critical thinking. The ANITA case teaches us that science is a process, not a collection of facts. It's a method for interrogating nature, testing hypotheses, ruling out alternatives, gradually building reliable knowledge. This process is messy, filled with wrong turns and dead ends, constantly revising its conclusions as new evidence arrives. Scientists get things wrong regularly. Experiments fail. Theories that seemed promising turn out to be incorrect. This is normal and healthy. It's how science works. But the messiness gets sanitized when science is communicated to the public. We want clean narratives with clear heroes, dramatic discoveries, revolutionary breakthroughs. We want certainty. Scientists, knowing how tentative most research is, speak carefully, but that carefulness disappears in translation. A might possibly suggest becomes shows, becomes proves. The gap between scientific practice and public perception grows wider, and this gap breeds distrust when people eventually realize that the certainty they were promised doesn't exist. Better science communication requires effort from everyone involved. Scientists need to engage with public communication, not leaving it entirely to journalists and content creators who might not understand the nuances. They need to learn to explain their work clearly, without oversimplifying to the point of distortion. This is hard. Scientific training doesn't typically include communication skills. Researchers are rewarded for publications in academic journals, not for clear public explanations. The incentives need to change. Journalists and content creators need to resist the temptation to sensationalize. Editors need to approve accurate headlines even if they're less clickable. This requires leadership willing to prioritize accuracy over engagement metrics. It also requires audiences who reward quality over sensationalism, who will read careful explanations rather than just skimming headlines. We, the public, bear responsibility too. We need to cultivate patience, to accept that real understanding takes time and effort, to resist the quick dopamine hit of sensational claims. But the deeper question remains genuinely open. Do parallel universes exist? Are we one reality among many? The honest answer is, we don't know. We may never know with certainty. The theoretical arguments are compelling. Quantum mechanics and cosmology both seem to predict multiverses under certain interpretations. The math is solid. The reasoning is sound, following logically from well-tested physics. But we lack direct observational evidence. We may never have such evidence if the other universes are fundamentally inaccessible, blocked not by distance but by the structure of reality itself. What we can say is that the question is being investigated seriously by respected physicists at major institutions. It's not pseudoscience. It's not wild speculation disconnected from established physics. It's a genuine scientific frontier where our best theories lead to surprising conclusions that we're still learning how to test. The investigation continues through observations of the cosmos, experiments with quantum systems, theoretical work refining our understanding of what these frameworks really predict. The multiverse might be real, or it might be a mathematical artifact, an interesting feature of our equations that doesn't correspond to physical reality. Both possibilities are on the table. What separates science from dogma is the willingness to follow evidence wherever it leads, to change our minds when the data demands it, to admit uncertainty rather than claiming knowledge we don't have. As for you, sitting here now, having spent time exploring this question, are there parallel versions of you making different choices, living different lives? Maybe. The physics allows for it. Quantum mechanics and eternal inflation both provide frameworks where such realities could exist. But it makes no practical difference to your life either way. You still have to make decisions, face consequences, navigate the reality you experience. Whether that reality is the only one or one among infinitely many changes the cosmic picture, but not your immediate situation. What matters is approaching these questions with rigor, honesty and wonder. Wonder at the strangeness of quantum mechanics, at the vastness of cosmic inflation, at the mathematical beauty of theoretical physics. Rigor in testing hypotheses, in distinguishing what we know from what we speculate, in maintaining standards of evidence. Honesty about the limits of our knowledge, about uncertainties and alternative explanations, about the difference between suggestive findings and definitive proof. The universe is astonishing enough without needing to invent discoveries that didn't happen. The real science of parallel universes, uncertain and incomplete as it is far more fascinating than any sensational headline. We live in a cosmos where particles can be in multiple places simultaneously until observed, where space itself can split into bubble universes with different physical laws, where the quantum state of the entire universe might branch into parallel realities with every passing moment. These aren't fantasies. They're serious possibilities that emerge from our best understanding of physics. Whether they're real remains to be determined. The investigation continues. Future observations might reveal signatures of bubble collisions in the cosmic microwave background. Quantum computing experiments might provide indirect evidence for many worlds. String theorists might find ways to constrain the landscape, making testable predictions. Or we might conclude that these questions lie permanently beyond empirical reach, residing in the domain of metaphysics rather than physics. Either way, the journey is worthwhile. Science is a human enterprise, flawed and fallible, but capable of astonishing achievements. We've mapped the cosmic microwave background, detected gravitational waves, imaged black holes, discovered thousands of planets around other stars. We've probed the quantum realm, tested relativity to extraordinary precision, built particle accelerators that recreate conditions from the first moments after the Big Bang. Every piece of knowledge was hard-won, wrested from nature through patient observation and clever experimentation. The question of parallel universes sits at the frontier of this grand project. It challenges us to think carefully about reality, about existence, about the nature of scientific knowledge itself. It forces us to confront the limits of observation, the role of mathematical reasoning, the boundaries between physics and philosophy. These are deep questions, worthy of our best thinking, deserving of careful investigation rather than premature certainty. If you found this exploration valuable, if you want to see more content that separates science from science fiction and gives you the real story behind the headlines, please hit that like button and subscribe. Science is a journey, not a destination. It's a process of asking questions, testing hypotheses, revising beliefs in light of evidence. We're all learning together, navigating a cosmos that keeps revealing new surprises, new mysteries, new reasons for awe. The viral story about NASA discovering a parallel universe was false, but the real investigation into whether parallel universes exist continues, conducted by serious scientists using rigorous methods, asking profound questions about the nature of reality. That investigation, that willingness to follow logic and evidence into strange new territories, that openness to revising our deepest assumptions about existence itself, that's the true wonder of science. Not the false certainties of viral headlines, but the honest uncertainties of genuine inquiry. Thank you for being part of that journey. Thank you for caring enough about truth to read this far, to think critically, to seek understanding rather than just accepting sensational claims. That critical thinking, that commitment to evidence and reason, is what will help us navigate the flood of information and misinformation in the modern world. Keep questioning, keep learning, keep wondering about the cosmos and your place in it. The universe is stranger and more beautiful than we can imagine, and the genuine mysteries are profound enough without adding fictional discoveries.